Okay, let's continue our discussion. So far, hopefully everybody understands that rate of the reaction, which is essentially the speed with which the reaction is taking place. Higher is the number, we say it's a fast reaction. Smaller is the number, we say it's a slow reaction. So this rate of the reaction is proportional to the concentration of the reactants. If you have a generic reaction, let's say A is becoming B, it's essentially the concentration of the reactant A, not B, that is going to decide the speed with which the reaction takes place. Because realize, closer those molecules are to each other, greater is the probability that they are going to interact with each other, and some of those collisions are going to be fruitful collisions, and they are going to give you the product molecules. So it's the concentration of the reactant which decides how the rate of the reaction is going to get altered. Now, if you remove the sign of proportionality, you have to introduce a constant of proportionality, and usually we use the small letter K, which is also called as the rate constant. Okay, now it's important to realize here that A, the concentration, can dictate the value of rate in a direct sense, in a linear sense. That means if you double the concentration of A, if A becomes twice of the initial concentration, then the rate also doubles. Rate doubles. That's one, that's one scenario. Another scenario could be that if you double the concentration of A, so if A becomes twice, maybe the rate becomes 4 times. Maybe the rate becomes 4 times. Or it could become 8 times, or, it just depends on the reaction, how it's going to proceed. So realize that we can't just say that it would be A to the K times the concentration, but rather also K times A to the power of M. Okay? This K, like I said, is rate constant. This is going to vary with the nature of the reaction and the temperature of the reaction. And the M that you have, the power that you are seeing, that is what is called as the order of the reaction. Order of the reaction. So again, for any reaction, A giving you products, we have written that rate is equal to K times A to the power of M. M is what is called as the order of the reaction. And this is what is going to decide how the rate is going to change each time the concentration of A varies. What I mean by that is, if you double the concentration of A, does the rate become doubled? Does it become quadrupled? Does it become 8 times, 16 times, whatever the case may be? Or maybe it doesn't change at all. That's a possibility too. So for the benefit, for this class, I would say you should focus on the order being 0, the order being 1, and the order being 2. So if that value of M with respect to A, if that happens to be 0, that would basically mean that you can increase the concentration all you want from, double, triple, whatever you want to, but that's not going to have any effect on the rate of the reaction, because the power then is going to be 0. So essentially you would say that rate is going to be equal to K, A to the power of 0. And since this factor is going to become 1, you would say the concentration is not changing the value of rate. On the other hand, something like first order would mean that if you double the concentration, so let's say that becomes 2 times, so A becomes 2 times, A becomes twice A0. A0 is the initial concentration. Then that would mean that it's going to be twice the value that you started with. Likewise, if it's a second order, then if you double the concentration, the effect on the rate would be that it gets quadrupled. If you triple the concentration, maybe it becomes 9 times, so on and so forth. What really is important for you to understand is that you cannot just, come up with the value of M theoretically. You have to run an experiment to see how that reaction is behaving. So you cannot deduce that from the coefficients of the balanced equation. So if you, for example, if you had the previous equation that we had N2O5, that was becoming NO2 plus half O2. So you can't just say, because if you have to balance it, this is 2, this is going to be 4, and this is going to go away. So you can't say that because this is 2, then the order with respect to N2O5 is 2. It may or may not be. It really depends on the reaction. So until and unless you have run some experiments, you can't predict the order of the reaction. It must be determined experimentally. Hope that's crystal clear. So you can perhaps envision that if you had a zero-order reaction, the rate law, as it's called, which basically puts in the rate of the reaction into perspective with respect to the concentration, it's going to look like this. And so you would say that the rate is going to be equal to K. The rate law for a first order reaction is going to look like rate is going to be equal to K times A to the power of 1. On the other hand, if you consider a second order reaction, the rate is going to look like K times A squared. Now, I told you earlier that rate is change of concentration, change of molar concentration per unit time. So hopefully you can see that the units for rate are moles per liter per second. So hopefully you can see that for a zero-order reaction, the units of K, which is the rate constant, will come out to be moles per liter per second. On the other hand, if you were thinking about a first-order reaction, you would say, well, rate is moles per liter per second, and the molar concentration of A here is moles per liter. So the moles per liter and the moles per liter will get cancelled, and the units of A happen to be just per second. And if you do the same thing for a second-order reaction, you can say that rate again is moles per liter per second. K is, of course, the units. And now you have moles per liter, and you're taking a square of that. So moles per liter, and one of these will cancel. So you can say that the units of K are going to be liter per mole per second. What does that tell you? That tells you that the units of K are dependent on the order of the reaction. And that is what gives you information on what the overall units are going to be. In this case, of course, we are dealing with just one reactant, but this is applicable to multiple reactants as well. So the question is, if order of the reaction is what is telling me, is what is going to give me information on K, using which I would be able to determine, what the overall rate would be, or I could determine the value of rate constant, as the case may be. How do we figure that out? So let's take a quick look. Since we know that rate is going to be equal to K times A, and let's say M is the order. Usually in questions like these, you would be given concentration, so you would be given some experimental evidence. You would be given what the rate was found to be at a specific concentration, and what the rate was found to be at another concentration. So those numbers would be provided to you. Based on those numbers, you can derive for yourself, you can write down for yourself rate law for both of the concentrations. So you can safely say that rate 1 is going to be equal to K times concentration A1 raised to the power of M. Likewise, you can also say rate 2 is going to be equal to K times A2 raised to the power of M. Now these are two equations. I'm just going to call them 1 and 2, and you can do A and B, whatever you want to. And then just go 1 divided by 2. Or you could do 2 divided by 1, whatever you're comfortable with. It's going to give you the same value. Let's say we do 1 divided by 2. So rate 1 divided by rate 2 is going to be equal to K A1 raised to the power of M divided by K A2 raised to the power of M. K and K is going to get cancelled since it's dependent for that reaction. So hopefully you can see that since the rate 1 A1, rate 2 A2, these were values that were experimentally determined, you should be able to determine the value of M. Let's see if we can actually apply this to a reaction. I'm showing you a reaction where acetaldehyde is going through, it's a decomposition reaction, one becoming many. It's a decomposition reaction, so acetaldehyde is getting converted to methane and carbon monoxide. And you're given various different rates and you're given various different concentrations. And you have to figure out the reaction order for this reaction. So you can pick, in a situation like this, you can pick any two experiments. So let's say this is experiment 1, this is experiment 2, this is experiment 3, this is experiment 4. Okay, and I pick, let's say, rate 1 is K times the concentration of acetaldehyde, CHO1, raised to the power of M. So I'm going to say that rate is 0.085 moles per liter per second is equal to K. Concentration is 0.1 moles per liter because it's molar, and M is what we are trying to figure out. So that can be said for experiment 1. You can write down an experiment 2 as well. You can say that 0.34 is equal to K times 0.2 raised to the power of M, right? So I'm using experiment 2. And then we are going to simply say that you take, this is 2, this is 1. Let's try maybe 2 divided by 1. 2 divided by 1. What would happen? 0.34 divided by 0.085 is equal to K 0.2 raised to the power of M divided by K 0.1 raised to the power of M. This goes 4 times. This is 4 folds. So you can say K and K cancels. You can say 4 is equal to 2, because these are both decimal, so the decimal cancels off. 2 raised to the power of M is equal to 4. Can I write 4 as 2 square? So if the bases are the same, then the powers must be equal to. M comes out to be 2. That means this is a second order reaction. Of course, another way that you could determine the math for this is you could simply take the log. So you could say taking log of both sides, log of 4 is equal to M log of 2. This number comes out to be 0.6020 on my calculator. Log 2 comes out to be 0.3010. And so M becomes 0.6020 divided by 0.3010, which comes out to be 2. So if you can't see exponents, you have to be able to figure out logs, whichever you're comfortable with, you can do that. But those are two methods that you can show your math if you have to. All right, let's go forward. So that's what I'm showing you here. Since the value of m, the order came out to be 2. Now you can write down the overall rate law as rate is equal to k times acetaldehyde raised to the power of 2. Realize earlier we had a generic expression that rate is equal to k times acetaldehyde CH3CHO raised to the power of m. But now we have defined that value of m, and we have defined that to be 2. Now, given this new rate law, realize what all can be done. Since we now know the exact expression of the rate law, there are a couple things that you can do. You can pick one of those 4 experiments that were listed. You can determine the value of, pick out the value of rate, pick out the value of the concentration, and you can figure out the value of K, right? Another thing that you can do is, once you have figured out the value of K, you can simply pick up any hypothetical concentration and determine what the rate would be at that point of time. Alternatively, you can figure out, come up with what would the concentration or what should the concentration be if the rate happens to be, and you can give a number for that. So realize here that essentially we have 2 things going on. You want to make sure that you realize that getting the complete rate law expression for your reaction is a very, very powerful thing, because you can determine boatload of information out of that. So let's perhaps take information from this question and take it forward. So I'm going to just slide back. So one of the experiment 3 was 0.76, and the value for the concentration was, this was rate, and this was 0.3 molar. So I'm going to just plug in this number 0.76 K times 0.3 square of that, so you can say 0.76 is equal to K times 0.09, hopefully. So K is equal to 0.76 divided by 0.09, which is going to come out to be, I'm going to plug these numbers in my calculator, and it comes out to be 8.44. Now, what should be the units of K? Recall the way we calculated early on. Your rate is moles per liter per second. Your concentration is moles per liter, and you're taking a square of that. So this should be 1 mole per liter cancels off. So the units of K should be liter per mole per second for this particular system. Now that you have the value of K, you know how fast the reaction is going to go. You can simply plug in any concentration under the sun, and you can predict what the rate of the reaction would be. You no longer have to carry out experiments each time for its measurement. So while we are at it, let's just work on that too. Maybe what would happen if the concentration is, let's say, 2 molar. Okay, my acetaldehyde concentration becomes 2 molar. Or you can make it more, interesting. 2.22 molar. 2.22. Let's plug in that. It's just a matter of plugging in. Plug and chug. Rate is equal to 8.44 liter per mole per second, and we are going to multiply that by 2.22 square of that, and of course that's going to be moles per liter, and square, each square, so 1 liter per mole, 1 liter per mole is going to get cancelled. Your units overall will be moles per liter per second, and on my calculator I'm punching in 8.44 times 8.44 times 2.22, and I'm supposed to take a square of that, and I'm getting a value of 41.59 moles per liter per second. That is my rate. So rate of the reaction is 41.59. Okay? All right, let's go forward. So over here, I guess I picked experiment 1. I'm just showing you the math for that. Experiment 1, and notice our value then came out to be 8.5, and I showed you hands-on experiment 3, which came out to be 8.44, so it's pretty close. And then here I'm trying a concentration of 0.55. Rate was calculated to be 2.6 moles per liter per second. Realize as we are increasing the concentration, so I used 2 molar and my value came out to be 41.59. When I used a value of 0.55, the rate was 2.6 moles per liter per second. And just a couple slides ago, when we started this discussion, I said that rate of a reaction does depend on the concentration of the reactant. Higher the concentration, most likely the rate is going to get affected by that. So notice I'm changing the concentration and the rate gets changed as well. All right? Let's see how it would get affected if I didn't have just one reactant, but rather 2 reactants. So I have A moles of A reacting with B moles of B to give you some products, okay? So now, since both A as well as B are going to participate in the reaction, your rate expression, your rate law must incorporate both of those. So your overall rate law, since rate is going to be proportional to the concentration of A, with respect to the order with respect to it, it's also going to be proportional to B with respect to order with respect to it. And so now when you combine both of these equations, you say rate is proportional to A raised to the power of M, which is the order with respect to A, times B raised to the power of N, which is the order with respect to B. So now when I remove the sign of proportionality, I have to introduce a constant of proportionality, and my rate law starts to look like this. Rate is equal to K times A raised to the power of M times B raised to the power of N. And if you had to determine the overall order of the reaction, how would you determine that? You would simply add the powers together, the M and the N together. So M plus N will give you the total order of reaction. Understand? M is the order with respect to one of the reactants. N is the order with respect to the other reactant. When you add the two together, you get the order with respect to the overall reaction. And so if you had to determine essentially how it's going to go, how can you determine the values of both M and N, it's going to be pretty much similar to what we did earlier, writing the rate laws and then comparing them together, but you will have to do that for 2 separate equations. So you have to do that twice. So how do we go about it? Please understand that if you have a rate law that looks like rate is equal to K, A times M, B times N, so you would be able to write a rate 1 with 2 concentrations and a rate 2 with 2 concentrations, and essentially you would be able to you would be able to take a look at the values that are given to you. Again, those are going to be experimental values. The way I want you to look at it, or the way I want you to select the experiments, is I want you to keep one of the concentrations constant. So pick those experiments in which maybe the A is constant, so A1 and A2 are exactly the same value, and maybe B1 varies. The advantage of doing that would be that at any given point of time, the K and the A and the M is going to cancel off. So you would be looking at rates with respect to B only. And if you do the same thing for keeping B constant the second time and varying A, then again you would be looking at the relative rates of 1 and 2, but now with respect to concentration of A1 and A2 alone. So it comes in pretty handy if you select experiments a little bit, strategically in that sense. So let's take a and see if we can apply that. The problem is that we have T-butyl bromide. Those of you who will continue on to organic 1 and 2 would deal with the substitution reaction, essentially. We would be studying that in good detail, but right now just go with the name. We have T-butyl bromide that's reacting with hydroxide to give you T-butanol, and bromide is released in the system. I have been given 5 different experiments where I'm varying T-butyl bromide and I'm varying the hydroxide. Notice in experiment 1, 2, and 3, essentially the concentration of hydroxide does not get changed. The concentration of T-butyl bromide is the one that varies. So hopefully you can see that you can either use experiment 1 and 2, or you can use experiment 1 and 3, or you can even use experiment 2 and 3. Those are the 3 possible combinations to figure out one of the orders, the order with respect to the T-butyl bromide. And if you wanted to compare, if you wanted to figure out the order with respect to the hydroxide, you can, because then you would keep the T-butyl bromide constant. You can either use experiment 4 and 5, or you can use experiments 2 and 4, or you can use experiments 2 and 5. Just ballpark, if you take a look, if you just compare, you can see that you are varying hydroxide concentration, but the rate is not getting changed. So that hopefully gives you an idea of how the numbers are going to look like. So, but I'm still going to go over the math to make sure everybody's on board. The question is that we have to determine order of the reaction with respect to both the reactants. We have to then write down the rate expression and find the overall order of the reaction. So first and foremost, you must go with the fact that we have here rate is equal to K times T-butyl bromide, maybe M times OH raised to the power of N. That is my generic rate law that I'm going to begin with, and I'm going to plug in specific experiments to get my overall answer. Okay, I want to keep the values in front of me, so I showed you that the rate can be written as K T-butyl bromide Br and raised to the power of M times hydroxide raised to the power of N. And now we have to determine the values of M and N first, because we have to determine the order with respect to both the reactants. So again, you can pick up any. I'm going to pick up 1 and let's say 3. So hopefully you can see that you will be able to write down rate 1 is equal to K T-butyl bromide. There's a C missing here. Br. I'm going to just say 1 for the first concentration. Hydroxide is 1 as well. So let's start plugging in the numbers, maybe. So 0.005 is equal to K times 0.5, that's right here, times hydroxide is 0.05 raised to the power of N. So this is the experiment I read, and I said third, right? So rate 3 is what I'm after. So rate 3. That's 0.015 equals K 1.5 raised to the power of M 0.05 N. And then just go 1 divided by 2 or 2 divided by 1. If you think that's simpler for you, okay, let's just do that. It really doesn't matter. Your dry lab will give you good practice for this, really good practice. And so you should be set for the test. Just working on the dry lab. M 0.05 N. These two cancel off, K cancels off. Hopefully you can see that this should be 3 times, and 3 is equal to 3 raised to the power of m. If the bases are equal, then the powers have to be equal, so you can say m is equal to 1. We know the value of m now. What do we do next? We would figure out the value with respect to the hydroxide the same way. And now we are going to do the same thing with respect to the hydroxide. So how do we do that? Let's pick experiment 4 and 5 for simplicity maybe. Again, you can pick whichever. I'm just showing you the math, rate 4, just to, show you. You can hopefully already see that as you're changing the concentration of hydroxide, no change occurs in case of the rate. So rate 4 is 0.01 is equal to K times 1 raised to the power of m, 0.1 raised to the power of n. Likewise, 0.01 K to the power of, we have the T-butyl, which is m, and 0.2 raised to the power of n, and simply then divide. So this is, let's say 1 and this is 2, so 1 divided by 2, 1 divided by 2, which will give you 0.1 m, 0.2 n. These two cancel, K cancel, 1 cancel. So you can see 1 is equal to half raised to the power of n, which basically means that n should be equal to 0, because anything raised to the power of 0 is going to be 1. So you can write this as that, and that would mean that the value of n is 0. Well, what does that mean? That means that the overall order, it's going to be m plus n, which is 1 plus 0, which is equal to 1. So your overall order is 1. M came out to be 1, n came out to be 0. And if you had to write down the rate expression, you would say it's going to be rate is equal to K times T-butyl bromide, Ch13-Cbr, raised to the power of 1, hydroxide, raised to the power of 0. That is your overall rate expression. So make sure in the dry lab also, once you have determined the value of m and n, you take the time to give me the overall rate expression, for that particular reaction. All right. So hopefully you're able to see that given a rate and concentrations experimentally, you can determine the orders with respect to specific reactants. You can determine the value of rate constant. You can determine the value of rates at any specific hypothetical concentration. Okay. Let's perhaps, I want to do one more problem. It probably is not going to be in your PowerPoint slide, but it just kind of brewed up in my head. So I'm going to include one more problem in this webcast, and we'll take it from there. So you're given this problem. You're given a reaction where oxygen is reacting with 2 moles of NO to give you 2 NO2. You're also given that the order with respect to, so these are experimentally determined numbers, not the stoichiometric coefficients. So this information is provided that the order with respect to oxygen is 1, with respect to nitrogen monoxide is 2, and there are 3 experiments, 3 scenarios. This is 1, this is 2, this is 3. And you're asked essentially which one of the 3 is going to have the highest initial rate. You're given oxygen, which is the homoatomic, so both blue, and NO is 1 blue, 1 red. So you have to tell which one will have the highest initial rate. Hopefully you can see here that you would be able to write that rate of the reaction is going to look like K times oxygen raised to the power of 1 and NO raised to the power of 2. So if you consider the 3, if you compare the 3, hopefully you can also see that every single one of them has same number of molecules total. So for instance, you have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Oh, I didn't put another one. 6. And you have 6 in C as well. So the total number is same. In case of A, you have those in the ratio 1 to 1. In case of B, you have more of the oxygen gas. So you have 4 of oxygen, you have 2 of nitrogen monoxide. And in case of C, you have greater concentration of NO. Now realize, since the concentration of NO essentially has a order with respect to it is 2, that basically means that if you have a greater concentration there, the effect is going to be larger on the rate. So in this case, you can envision that C is the one that's going to go with the maximum initial rate.